Hopefully you all had a good first weekend. Are there any questions before I get started? Yes?
The readings that you posted, are those?
They're not yet assigned.
Okay.
Right. There should be a reader ready by the end of the week, and later today I will post your first homework assignment and any reading assignments. But you're welcome to look at them. We'll be covering that material probably next week. I left off on Friday with not quite enough time to show you how to install R. And so did anybody have a chance to do that this weekend? Oh, good. Great. So I'll give a quick run through for the rest of the class. And those of you who have installed it, if there's something that I've left out that is an important, in fact, if there's anything that I've left out that's important, and especially for those of you who are Windows users, I'm a Mac user, and therefore I'm not quite as familiar with the procedures for Windows. So I just thought I'd quickly do a little demo. I'm connected to the wireless, but I've also saved a few tabs in case the wireless gets slow. Question? Can't hear me. Let me turn this up. How is that? Is that better? How's that? Even better or no different? Yeah, that's the problem is my shirt's not really stiff, so the mic bends out. Here, let me try. How's that? Is that better? Okay, good. All right. Is it too loud? Shall I turn it down? No. Okay. So go to your favorite search engine. I'm here at Google. I mentioned on Friday you type in the letter R, hit return. Let's see. Am I getting it? There we go. The very first result returned is the R project for statistical computing. That's what you want. And so you can then click on that. And up pops some of the graphics that you can make in R is the centerpiece. And what you really want to be looking for is the bar along the left-hand side. And it says download packages CRAN. That's a repository for R's. I believe every 6 months they come out with a new release of R. So rather than having to go to one site, R has mirror sites all around the world. And you want to pick one that's close to where you live. And if we scroll all the way down to the USA, you see that there's one at the University of California, Berkeley in the College of Natural Resources. There's another one at UCLA. And we click on that. And it comes up with 3 options. So depending on the computer operating system, you can choose Linux, Mac OS X, or Windows. So I'll choose Mac OS X. And at that point, what you want to do is, notice that it says that this runs on Mac OS X release 10.5 and higher. If you have an older machine or an older operating system than that, then you'll have to scroll down and worry about what to do there. But essentially, for those of you with relatively new operating systems, you want to pick R-2.11.1 and click on it. Then you have an option. I like to save them to a directory called downloads. So I say save, and here's my downloads directory. And as you can see, I already have it saved. So I'm not going to bother to download it since it might take a little bit of time. And then all you do is open your Finder, go to your downloads directory, and as you can see, I have a lot of downloads. Hang on, let's go all the way past it. So many that I can't even. There we go. There it is, right there. And so we just click on it and go through the installation process. It's as simple as that. You can do the usual. You all, I'm sure, know how to install software on your machines. As you can tell, we got here without having to pay any money. It's a open source free software, and you just have to agree to the license agreement, and then you can start doing the installation. I'm not going to do the installation because I already have it installed. But just continue clicking through, and R will be installed for you. Okay, so I'm going to now cancel this and go back here to R and just really briefly, if you have Windows, you just do a very similar thing. You click on the Windows option. And basically, at this point, if you just install the base package, what's very unique about R is that there are all sorts of libraries that are contributed by R users from around the world. And so you can have access to the most current statistical methodologies through these packages that people contribute. So you can have an option to not only install the base, but if you would also like to, you can install all of the contributed packages. And so, let's see, download R 2.11 for Windows right at the top, and that's a .exe file, and proceed from there. I'm not going to do that, but you, again, save the file and double-click and get it installed. Those of you who did it, there were a handful of you who did it over the weekend. Was there anything in particular that you want to comment on? Yes? You have a question? Yeah, so we can answer, very good question. Should I run 32-bit or 64-bit R? There's actually a question right there. And we can look to see. For most users, especially beginners, we recommend using the 32-bit build. That will still run on your machine. So you can read through this and make the decision as to what you want to do. I would go with their recommendations, though. Who else was going to? You had your hand up. Were you going to make a? No, you didn't. Anyone who installed it this weekend want to make a comment? Was it easy? Yes, it was It was really easy. You thought so too?
I did.
You did. Have you tried to actually run it?
No.
How about you? Have you actually? Okay. So the next step is to actually try to run R. So in my case, if you look at my toolbar on the bottom, I have this little thing, it's a little hard for you to see with the resolution of the screen, but there's a little circle with a letter R in it, and I can click on that, and the R console opens. So now we're going to transition into a tiny, very short lesson about R. Notice all these messages come across at the beginning when you first open up this little R console, and see that I do have 2.11.1 installed, and that was released on May 31st. So there's a little greater than symbol, and that's the prompt in R, meaning you enter your commands at the prompt. So we're just barely going to get started today, and we're going to continue more in lab tomorrow and also in class on Wednesday. So I just want to get you a little bit used to using R. And so think of it, to begin with, as a calculator, a really souped-up, fancy calculator. And so anything that you sort of punch into your calculator, you can do the same with R. And maybe by the end of this class, you will start using R as a calculator. So I can say, okay, what's 2 times 3? And it comes back, I hit return, hit enter, and it comes back with 6. So I can say 2 times and accidentally hit return, and it comes back with a plus sign. That plus sign's important. It says, you know what, you haven't created an expression that I know how to evaluate yet. It looks to me like you're halfway through doing something. So if you'd like to continue, that's what the plus means, continue. So I then put my 3 in and then hit return, and it says, okay, I can do that computation. I'll do that for you. By the way, what I'm going to do is post a transcript of this session that's with comments on it on BSpace at the end of each day whenever we do this kind of thing. So R also has built into it well, I typed in pi. Let me ask you what you think this is. So it actually has pi, or a representation of pi, not to so many digits, but to many digits, stored in it. And we can use that as part of our computations. So I can take pi and add 1 to it and get 4.14159. There are all sorts of other functions like a calculator would have. So I can take log of 100. So I just enter log. Did you notice as soon as I put the open paren, it stuck the close paren for me, and then I can type the number or whatever I want to take the log of. I'm going to change the screen a little bit to make this is smaller, but you will then be able to see what I'm doing. Here, let me, you'll be able to see what I'm doing a little better. Okay. I was trying to get rid of that. Okay. All right, so what do you think this will return when I hit enter? What's going to be the value that is going to return? It's 4.6 something. What does that mean? What does that tell you? Think back to logs. It's not base 10. It's the natural log. That's the default. Most statisticians work with natural logs. And so the default when you type log is to get the natural log. If you want log base 10, you call the function log 10. So log 10 of 100 returns what you might have first guessed, 2. Okay? Then you can start building up, you can start building up other computations using these variables or these constants like pi. So I can take the sine of pi over 2, and I get 1 back. Does that sound right to you? So there's sine, cosine, log, exp for exponential, all the usual plus many more. So order of operations is important. So if I say 1 plus 2 times 10, what do you think the response will be? I heard some of you say 21, that's right. As opposed to if I say paren 1 plus 2 times 10, and that's 30. So you can, the order of operations is exponentiation, then multiplication and division, then addition and subtraction. And you can do something like log 10 of 100 plus, so you can build up quite fancy computations or calculations. Sine pi over 2 times 15. And that's 17. And if I just change the parentheses a little bit, or change the order of operations by putting parentheses around log base 10 of 100 plus sine pi over 2, put parens around that, and then multiply it by 15, I get 45. Okay.
Yeah, how do you call your last function? How do you do that?
Oh, thank you. What I just did was I used my up I have the little arrows left, right, up, down. And lots of times we want shortcuts for typing. And to do that, I can hit the up arrow, and it brings back computation. So I can bring back the last one. I hit it again. I bring back the one before. This is really handy, especially because we're often wanting to try something out, say, oh, that's not quite right. Let me just fix it a little bit. And you can keep doing this. So I can go all the way to the third prior computation, modify it, and then hit return, and that will then execute. Thank you, Mike. Are there any questions? Any other questions? Yes?
How do you switch between radians and degrees?
Okay, I don't know off the top of my head, but we'll now go to the help functions that are available. So if I look at, help, and then we can also talk about the error messages that you might get in R. I did help sim instead of sign, and it says, sorry, I don't have any documentation for that. It didn't recognize SIN. So the question mark is a way of asking for help, and I can ask for help on any function, and it opens up a little browser for me. And so it talks about, at the top is a description of what the function does. So it says we've got all these trigonometric functions for sine, cosine, tangent, etc. And it talks about how to call them and what are the arguments. So angles are in radians, not degrees, i.e. right angle is pi over 2. I think you must need to convert them, and so there's probably a function. Usually at the bottom, there's something that says see also. I don't see that here. Let's do help on radian, or radians. Nope. I'll have to get back to you on, so very important lesson is that there is help in R, and sometimes it's hard to figure out how to find the help you need. And so one thing that you can do is bring up Google again and go to Google and start by typing the letter R and then say sine radian to degrees or something like that. And this is so common that unfortunately it's not bringing up something specific to R. We can let's see. Let's try this again. Nothing good. R sine degrees.
Yeah?
Yes?
No, function, you could divide by 2 pi.
Yeah, I was assuming we could actually then multiply by whatever. Yes, I was assuming, yes. Thank you for pointing that out. There's always ways around it where you can do your own computations in R. That was Mike in the back. But, well, to be continued. Let me get back to you on a good search to figure out how to do that conversion. But yes, as Mike says, you can do your own conversion using the calculator in R. But I believe there's also a way to do that conversion with a function call. So variable names, so far I've only used x, and I can, if I want to multiply 2 times x, I might sometime type in 2x, and it says, oh, I'm sorry, I don't recognize 2x, and that's because there's no, if I'd said 2 times x, that would have, it also says it doesn't recognize x, and that's because I'm ahead of myself. We can save results from computations or by assigning them to a variable such as x. So here's x equals 1 plus pi. Now in my workspace, I have a variable called x. And if I type in x and hit return, I get the value back, 4.14. So if I try to look for the variable 2 or multiply 2 times x, it thinks that I'm looking for something called 2x and says, hey, I don't understand that. If, on the other hand, I do 2 times x, it multiplies my value of x by 2. So there are only certain variable names that are allowed. So I can have x2. So a variable name has to start with a letter. So I can say x2 equals 3 times x, and then I can look at what x2 is. I can change x. I can reassign it. X is equal to 150. And then the question is, what's x2 now? x2 is still what it was the first time I assigned it. It doesn't change. Okay? So I'm going to do one more thing before we go on to talking about graphical representations of data. And that is, it's really important to not just leave you with R as a big calculator. R essentially is a vectorized language. What that means is that even the variable x here that I've created, it's treating as a vector. A vector is just a list, or it's just a collection of, let's say, numbers. It could be logicals as well, but let's for now say it's a collection of numbers that has an order to it. So I can create a vector by assigning x to, here's a function, C for catenate, 1, 12, minus 2, 100. Now if I look at x, it's a vector with 4 elements. In that order, the first one is 1, second's 12, third's minus 2, fourth is 100. Is everybody with me? So we like to use vectors as statisticians because we think of x as like all of the measurements, like the heights of everybody in this class, or the time you got up this morning, that sort of thing. Those could be our vectors. And then we can operate on those vectors, like double everything by saying what's 2 times x, and that multiplies each element of x by 2. Or what's x plus 3? That adds 3 to every element in x. Or what's pi x, let's try x divided by pi. That divides every element in x by pi. Yes?
Is there a way to switch it over from like decimals and fractions?
No. No. This is the way, so the question was, is there any way to switch it from decimals to fractions? No. However, you can print it out with fewer decimal places if you want to. So I'm going to now show you a couple functions in R. So functions are really, if you understand functions from a mathematical perspective, then it's really easy to understand how to use functions in R. You just give the function name, paren, the arguments to the function separated by commas, then close the paren. And so if I wanted to, for example, add up all the elements in x, I use the sum function, and I call the sum function and pass it as its argument my variable x. And so this is going to add up all of the values in x, and I get 111. I could also call the mean function, and I get 27.75. That adds them all up and divides by the number. You can also create compound functions by having the result of one function be the input to the next function. So in other words, I could take the sum of the absolute value of x. And so because if you look up there, I have an x has a -2 in it, then I will get a different result when I sum these up. I now have 115 instead of 111. So that's basically just a really quick intro to R, and you see how easy it is to use if you understand how to call functions, or if you understand the syntax for functions, and think about operating on sets of numbers that have an order, then those are 2 of the main concepts in R. So you might ask, okay, how do I get out of this? How do I quit R? There are several ways to do it. You can come up here and say quit R, but also just to to show you other ways, you can also call the Q function with no arguments, and Q stands for quit. Or you can hit the red button at the top of the console. And so it will ask you, do you want to save this session? Typically, I would suggest that you don't save your session because if you're doing lots of work and have lots of variables in there, they'll still be there the next time you start R. So it's up to you if you want them to be there or not. But if you constantly save your session, you'll get a lot of stuff in there. I'm going to cancel for right now and show you one other thing, is that over here, if I click on that little sort of stripy flag-looking icon, over here are all the commands that I've entered in this session. And this is my history. I can save this history so I can use it again. I could delete or clear everything, but it's a way to keep track of your session. Okay, so now I am going to quit. I'll call the quit function. Oops. And I will not save, and now I'm out of R. Yes? Oh, there's a difference between clearing the history and clearing out your workspace. So clearing history is just throwing away the memory of all the commands or expressions that you used, and you'll still have everything. You'll still have all the variables in your workspace. Saving your workspace says every single object that I created, I want to keep. Yes? Clear everything, meaning all the objects? When I said quit, it asked me if I wanted to save, and I said no, then they're all thrown away. So if I go back into R now, those guys, X will no longer be there. I'll say type in X, and they'll say, hey, I can't find X. What are you talking about? And that's because I didn't save these things. Other questions? Yes?
Sorry, the Windows version looks a little bit different. Can you click the history?
Yes?
Can you click on?
I clicked on the little, it's right in the center, the green and yellow striped boxy looking thing. I can look at it after class. I don't know what it looks like in Windows. Okay. Let's get on to our formal material that we're going to cover today. So on Friday, just as a quick recap, we collected data from everyone in the class, and we saw that there were different types of data. There was quantitative and qualitative, and then within quantitative, we had both interval and ratio, and within qualitative, we had nominal and ordinal. Now today, we're going to restrict ourselves to looking at quantitative type information, and we're going to talk about how you might summarize data. So really quickly, a slight side tour is why are we using R? It's because R is a statistical programming language, so it's actually designed to do statistical computations efficiently and also to do the kinds of statistical computations that statisticians are interested in. It's a very high-level scripting language. It's not like a compiled language. As you saw, what we just did is you enter commands at the command line, hit return, and you immediately get your response back. So it's very useful for doing exploratory data analysis and for also iterating the process of analyzing your data. In addition, a lot of the methods, the statistical methods, there's been a lot of care put into the underlying algorithms to do those. If any of you are already familiar with things like fitting linear models or least squares and regression, R uses very sound algorithms, numerical algorithms, to do those kinds of computations. And as I mentioned already, the contributed packages make it really easy for you to keep up with the latest types of statistical methods. So we've already done the installation and got started with R and looked at variables and functions. And now we want to go to our very first case study. I think no one mentioned you didn't have trouble seeing. Is that better? Yes. Yes. All right. This is an ad from I believe the 1940s, and it's a photograph, or it's not a photograph. It's a physician. It's a drawing of a physician recommending that you smoke Lucky Strikes. You know, today not only today would a physician not recommend that you smoke, but today you can't even advertise for smoking cigarettes. It wasn't until 1964 that the Surgeon General of the United States came out with a recommendation that smoking causes lung cancer, heart disease, emphysema, and may complicate pregnancy. So I have two questions for you. What do you think the Surgeon General needed in order to come up with that statement? It's like, yes?
Information that proved a correlation between smoking and all of those things?
We have information that proved a correlation between smoking and all of these things, lung cancer, heart disease, etc. We're going to get to this later in the semester, but a correlation just says there's a relationship between those. It doesn't say that one causes the other. So you actually needed some sort of stronger evidence that smoking caused cancer. So you're partially right in that you need that correlation between smoking and these diseases, but that doesn't seal the deal. Part of the issue is that ideally there would be experiments run where you would assign some people to smoke and other people to not smoke, and then see if those who smoked got cancer at a higher rate than those who did not smoke. Why wouldn't we do such an experiment? Did they do such an experiment in order to come up with this conclusion? No, why not? Yes? It's not ethical, that's right. So instead of conducting an experiment where we are able to control all sorts of factors and have these two groups very similar aside from whether or not they smoked, we can't do that. We can only observe people who smoke and observe people who don't smoke and see what the incidence of cancer is. But they do conduct experiments on animals and did find that smoking did cause cancer among animals. And they did look at observational studies of these large populations of people smoking and non-smoking, and saw that there was a difference in the prevalence of cancer between the two groups. And they did have a physical model as to why inhaling cigarette smoke or tobacco smoke might cause cancer. In addition to that, they had twin studies. These are much smaller studies, but they're studies of twins who, where one smoked and the other didn't, and saw that there's a higher rate of some of these diseases among those who did smoke. And so it was all of these separate pieces of information, or results from all of these different studies and experiments and the physical models, that at some point the Surgeon General said, well, in the 1960s, said, this is enough evidence for me to come to the conclusion that smoking causes lung cancer, heart disease, and emphysema. And now we all know that that's obviously the case. What's the difference between his statement about lung cancer, heart disease, and emphysema and the statement about complications in pregnancy? Yes, Eugene?
The idea that, they've seen multiple times where, if you smoke, you're almost guaranteed to get at least one of those three. but it's not necessarily a guarantee that if you smoke, you're going to have a pregnancy complication.
I'm not sure if they would guarantee that you get cancer if you smoke. But what is it that you're trying to, based on what you see up here, what is it about the
word
language? The word may, that's right. That's very different between it does cause it and the word may. And what were you going to say? The word may, that's right. And so why do you think they have the word may there?
Because they don't know if it's
You're right, they haven't made that same kind of decision. What were you going to say?
so complicated, just kind of vague as well. The word complicated.
That's true, complicated. There isn't a specific outcome that they're saying would be caused or may even be caused. So they're thinking that something not good might happen, and they're not actually getting very specific about it, and they're using the may, might. Yes?
Pregnancy is only 9 months.
Mm-hmm.
These might take 30 years.
So you're saying that a pregnancy is 9 months, and that's kind of a shorter window to be able to try and observe people and make some kinds of conclusions about the outcome? Is that what? Mm-hmm. Right. So before we go there as to why it might not, part of what you're also getting at here is that there's not enough conclusive evidence by the Surgeon General, and that might be one reason why. So this has been studied, this question of what's the effect on the unborn child due to smoking of the mother. And right now, if you are become pregnant and visit your doctor, they will basically highly, strongly recommend that you do not smoke and you do not drink and you do not take drugs while you're pregnant. In the 1960s, that was not the case, and there were studies of pregnant women, and one in particular was done here in Oakland, California, of mothers who were pregnant over several years. Not that each mother was pregnant for several years, but the mothers who entered the study came to Kaiser and were pregnant during this time period. And they took all sorts of measurements on the mothers and their children. Some of the measurements were how big was the baby when it was born. And in particular, we're looking at a very small slice of that data. We're only looking at the male babies, or we're going to look at the male babies and those that were single birth babies. In other words, they're not one of a twin or a triplet, and they survived 28 days. And we're going to be looking at studying the birth weight of these babies.
They survive like 20 days period, or they?
No, at least 28 days. Right. Right. And so typically in statistics, what we're wanting to do is compare the babies born to mothers who smoked while they're pregnant to the babies born to mothers who did not smoke. Right now, we're just going to look only at their birth weight. But let me ask you this. Why do you think we might want to restrict ourselves to looking only at male babies that are singletons and who survived at least 28 days? Yes?
Because male babies could differ in weight from female babies.
Because male babies could differ in weight from female babies? Yes?
I just wanted to say that you're just narrowing down the variables so that there's not so many variables that could mess with your results, basically.
That's right, we are controlling for other factors that we might think would affect birth weight. And one of those, as you just said, is male-female. And why would we think singleton versus twin would make a difference?
Probably bigger.
Singletons have more room, right? They don't have to share that space, and they tend to be bigger. That's right. And so we don't want to sort of complicate the issue of twins versus singletons in terms of birth weight. And then the 28 days says we're looking essentially at healthy babies that are going to grow up. And in fact, this study followed these babies until they were teenagers in high school. There was a lot of information that was collected on the mother and her child, and also her partner, the father of the child. Birth weight is the one we're going to look at today. Gestation is another one, which is, and so this is going to be the set of data that you'll be working with for your first assignment. The gestation is the number of weeks that the woman was pregnant. Parity is the total number of previous pregnancies. The mother's height and weight. The mother's smoking status, whether she smoked while she was pregnant or not. The mother's age, race, education level, income, and many more variables. So before we get too far down that road, we're just going to look at birth weight. There it is. That's the birth weight for all the babies in the study. What do you think? What do you think the distribution of birth weight is for the babies? So that's all the information. You've got everything. Does anybody want to make any statement about, this is in ounces, about the typical size of a baby? It's not very easy to analyze data that look like that, is it? You're up close. Maybe you can actually read it. Those people in the back don't have a chance.
No, I just want to say it would be easier to observe the trends if it was graphically represented.
Would it be easier to observe, let's say, the structure if it were graphically represented? Yes, it could very well be. And so that's what I'm going to show you is a rug plot. Has anybody ever heard of a rug plot? You have. Wow. What's a rug plot?
It basically has lines to show like how often one of the measurements occurs. And the darker it is, the more frequent it is.
That's roughly correct. What she said, I didn't bring my mic today, which is too bad, is that there's a tick mark for every baby, and it's located at that baby's weight. And so when there are a lot of tick marks close together, it looks like a thick line. So this gives you more information than, or easier way to summarize the structure of the birth weights compared to this set of numbers. So what I actually did was, since the birth weight was measured to the nearest ounce, in fact, to make this rug, I jittered the information a tiny bit to keep it from all falling on top of each other. So I added a tiny bit of random noise to every birth weight, so that, not so much so that it misrepresents their weight, but just enough so that a lot of observations that might be 120 ounces don't all fall and get plotted right on top of each other. Does anyone want to make any other statements about the structure of the data? So what are the kinds of things we might talk about?
There was a huge baby that was born. I feel bad for the mom.
Yeah, there was a huge, huge baby. That's 176 ounces, in fact. That's, what's that, 11 pounds? That's a big baby. And then there's some really tiny babies. The smallest one there is 55 ounces. It's less than 4 pounds. So now all of a sudden we can easily see the range of the data. What else can you see based on this rug? Yes?
You can estimate the modal weight,
You can estimate what's a modal weight.
the most frequent weight.
You can have a good guess at it. What would be your guess at what the mode is, the most common weight?
120.
120. And why do you say that?
Because a lot of the thicker lines are
There are lots of thick lines saying that they're but there are some thick lines around 101 as well. And there's some thick lines around 124 and around 144. Why do you think there's or do you think there's more than one mode? Yeah?
Yeah, there could be more.
There could be more. I don't mean to suggest that. I would just mean to sort of make you. There could be. Do you think so? Possibly. I've got him on the fence now. Before he was sure there was a mode at 120. How about anyone else here? So in a way, you want to, every baby's measured to the nearest ounce. In a way, you want to be able to sort of smooth out what you see. and sort of fill in the gaps of where there are no data. And that's, my jittering did a little bit of that. But it's hard to see if there are modes here because there's so much data and there are all these thick lines. But I pushed you. In fact, your first statement was actually quite good, that it looks like there's a mode at 120. All right. How about a distribution table? That's another way to summarize the data. That's where we pool together all the weights in certain ranges. I just picked these, 55 to 75. There are 20 babies. 75 to 85, 26 babies. 85 to 95, 56 babies, etc. Can you see more of the structure here? I think your suggestion about mode still is a little hard to tell, but maybe you can see it a little better here. Right? You see things increasing until it gets right around the 115 to 125 range, and then it drops off. So maybe your guess was actually quite good. It's still hard to see a lot of structure in the data by looking at this table or the rug plot. Essentially, what we're asking you to try and do is look at or create a statement about the distribution of birth weights that's helpful for us to think about in the future, or even now, just to summarize the babies from 1964. What's a simple way to summarize the different values, the different possible weights that these babies could take on, and what are really common weights, what are small ones? A distribution table is a start at doing that. And a density plot is another way to do that. And a density plot gives even more information. Here's a density plot made in R. The male babies born at Oakland Kaiser in the 1960s. Now we see the range roughly from 55 to 100. Now what this does is it smooths out the locations of the birth weights. And so, or it sort of averages neighboring ones to create this density plot. And so now how would you describe the distribution of birth weight? How about, I'll go back to you, who said you thought it might be unimodal with a mode around 120.
Yeah,
And that's, in fact, we see that, yes? Mm-hmm.
I guess the best way to describe it would be a bell curve, like we discussed.
You were ready to call it a bell curve. We did talk on Friday about how living organisms, when we take measurements of them, oftentimes these measurements follow a bell curve. This looks like that might be the case. Whether or not we go straight to the bell curve, what are some characteristics of this distribution? Is it roughly symmetric? Yeah, so about 120. So in other words, if we look to the right, if we could fold this distribution page, if it were on a paper and I folded it at 120, what's on the right and what's on the left look roughly the same, except what do you say about that? What might be some slight deviations from that symmetry? Anybody? Yes?
Well, you could possibly extend further on the right, whereas you can't go past 0, or it could be that more on the right side.
Yes, but do we see, so what you said is we know babies can't be 0. It's true, but we're a long way from 0. I'm not sure that's and these babies survived at least 28 days. So yes?
Seems a little heavy around 100.
Seems a little, you see maybe a slight lip there in the distribution. That's right. Do you think the two tails, are they roughly the same?
The tail on
I
the
hear
right
yes
is
and no.
shorter.
The tail on the right is shorter. What were you going to say? Same thing, or the tail on the left is longer? That's right. The tail on the left doesn't look like it trails off quite as much. Why might that be the case? Take someone else. Why might that be the case? Why might there be a sort of a longer left tail than a right tail? Someone in the back. What do you know about babies? aside from the fact that they're small. Yes?
It's not quite possible to have a huge baby, but it's quite possible to work on that.
Yeah, how do huge babies come about versus small babies? Small babies are immature, they're born too soon. Really large babies kind of don't happen. The mother just needs to get rid of them, right? She needs to give birth, and that happens. So, and in fact, if we talk about truncation, it's probably more likely there's the reason why we have a short right tail is that baby's only going to grow so big before it's going to be born. We could change the smoothing parameter, which is the way that how I average the neighboring values. And when I use a larger smoothing parameter, I get something much smoother. So that's sort of, it's really saying, hey, you know, I'm really gonna smooth out all these bumps a lot. And now I'm really getting something that looks normal. Well, that's because I'm smoothing it using some sort of normal information. Oh my goodness, you're getting antsy. Wait a minute. Don't go yet. Here's the distribution where I have a much shorter bandwidth. And I can sort of see much more of the individual observations. And what we want to do is choose between the smoothing parameters so we see the structure but not the individual results.